So welcome everyone to the MCRN Colloquium. It's great to be starting back up again this fall. So to kick us off today, we'll be hearing from Dr. Seth Cowall. Currently, he's a professor in the Department of Mathematics at the University of Georgia. He got his PhD in 2019 at the University of Delaware. And his research interests these days are mathematical biology, dynamical systems, environmental mathematics, and particularly mathematics and climate. So he's also a member of MCRN, and I'm very much looking forward to hear him talk about dynamical storage analysis, a computational approach to continuous systems. So thanks, Seth, and please take it away.
Okay. So all right. So right now I have my slides full screen, but I cannot see anyone. So if you have a question, you just have to speak up. So all right. So this is joint work between myself and Generic Zancy, also at the math department at the University of Georgia. Okay. So can everyone see my slides progress to this slide 2?
Yep.
Okay, good. Okay, so I'll just continue. Okay, all right. So first, what I'm going to do is talk about what I mean by dynamical storage, and just in a general sense, and then give some background and what has been done, and then set some goals as far as what we're trying to accomplish, and then we're going to talk about the process that we have come up with, which gets kind of messy, but it gets easier to understand once we give an example. And so right after I lay out the process, I give a very simple. I put it in. I put it to work with a very simple linear model. And then we discuss some complications with a nonlinear case. Okay, so let's see. I think I have something that's covering up part of my title, but I don't think you can see it, so let's not worry about it. Okay, so ecosystems, they're often modeled as compartment models. We have different equations, differential equations, and such things. And there's compartments, and there's flows of energy or matter or biomass in between them. And there's a set of tools known as network environment analysis. There's lots of literature on that, which is basically methods that are used to trace the energy and material flows through these compartments, and they use tools such as cycling index, storage analysis, which we'll be talking about today. But a problem is the applicability of these tools is limited by the fact that they're generally can only be applied to models at constant steady states. And in the real world, there's oftentimes things have environmental forcings on them, like seasonal changes, climate shifts, and other such things. So we have now methods for getting around that, which I will talk about. So okay, this bar is in my way. I need to. Oh, there it is. Good. All right, good. All right, so let's get at least start to think mathematically what we mean by storage, starting with just a very, very general linear made up example. So suppose we just have a linear system here, an ODE where we have dx dt equals cx plus z, where c is a square matrix full of constants. X is our state variable, and for each component of x, that's these are our compartments. And Z represents our sources, and these are these are all constants, and this is I'll just say material for whether it's energy or biomass or whatever flowing into the compartments. Okay, so we want to think of storage as the amount of storage in compartment XJ as the amount of material that resides in XJ for a long time. And for long, we'll say perhaps infinite, but I don't know. You could also think, well, until the next ice age. So maybe not literally infinite, but we'll just say a long time. And a question that we might want to ask is how much storage would result in compartment XI as a result from instantaneous input into XJ from sources and from flow into other compartments. In other words, what we just put into XJ, how much of that is going to stick around in XI for a long time? All right, so that's the hold on a minute. Slide down. Okay, that's weird. Okay, I must not have my my cursor on the slide. Okay, so now if C is constant, then one way we can figure out what's stored in each of the compartments of X is quite simple. We can just solve for the steady state, set the time derivative equal to 0, and then do some algebra. Just let's see, subtract. Well, once set the time derivative equal to 0, we'll just consider X to be X star for the steady state, and then solve until we get X star equal to negative C inverse Z. And I forgot to specify, let's also assume that C is an invertible matrix. Again, this is just a made up example. Let's rename this matrix negative C inverse to be S, and we'll call this the storage matrix. I mean, this since X is a steady state, this tells us what's staying in X for the long run. And let's see, the matrix or the entry Sij will represent how much storage is generated at compartment I as a result from one unit of input at compartment J. All right, if only life were always so simple, which it's not. Since it's not, we got asked the question, well, what about non-autonomous systems or nonlinear systems, which obviously this one doesn't qualify as. Well, we'll proceed and talk about those. Okay, so what has been done? All right, well, let's see. My collaborator, Generic Kazanci, is he's been on a few of these projects. There's something called dynamic environment approximation that was, let's just call that a coarse approximation that he did a few years back. And there's something called network particle tracking that he did with a grad student back in 2012. Let me just say this was an agent-based algorithm that what they did was okay. Well, one of the results from this paper is they applied their technique, this agent-based algorithm, to a nonlinear system, and they were able to come up with well, they produced a storage matrix for it we managed in the work I've done with Genera, and we managed to match the results using just ODEs. So I guess I'll just begin with the end in mind. It's also interesting to mention the flipbook environmental network analysis, where they discretize the continuous influence of abiotic factors. If you're interested in details, you can look these up. But anyway, our technique managed to do this in a much easier way. Okay, so this is how we dove in. This is how this is the beginning of how we describe our technique. So let's consider our system, just a general system, where we have a system of n equations, and each one is a derivative of compartment xi. And let's see, where we have our inputs and outputs, and let's call the zi's, let's call those sources, and let's call the fij, let's call it the flow rate from compartment j to compartment I. And this right here will be the sum of all the flows from every j into the specific compartment I. And let's call yi's the sinks out of I, and fji would be all the flows out of I into other compartments j. So I drew a little schematic here to help visualize these. So if we have a compartment I here, our source flows zi will be flowing in, yi will be flowing out, but fij would be the flow rate from compartment j to I, but fki would be a flow rate outward from I to k. Okay, so we start with a system of n equations. Each one we'll look up would be of this general form, and let's say that let's start just getting a general idea of how we would build a storage matrix. This is kind of maybe a half of a definition. Let's say our matrix Sij in a time period AB would represent the amount of storage created at compartment I over time A infinity by input into compartment J over the time AB. In other words, what goes into compartment J in the time interval AB. We want to know how much of that gets stuck in compartment I in between time A infinity. So that's generally what this means. But since we're interested in storage as a result from instantaneous input into compartment J, let's change the right endpoint to time t. Well, let's call this S of t, and have the right endpoint of that time interval t. And excuse me, I got my rights and lefts mixed up. Okay, the left endpoint to time t, and the right endpoint as time t plus h, and let's take the limit as h approaches 0. Okay. All right. So what we do to track which flows, the flows that start from a certain compartment, and where I'm sorry, to track the material that starts from a certain compartment and where that ends up in long sticking around for a very long time. What we do is we take each compartment and we divide that up.
Your slides disappeared.
They did. Oh, okay. They disappeared. Okay, let's see if I can get them back. Okay, file folder. Okay, you can see them now?
Yep. Yeah.
Okay. So did they disappear when you saw this?
Yeah, I think that's.
Okay. Okay. Yeah, there was a window that said you were sharing another application window. So that must have disappeared when you said that. So, okay. All right. Just, I don't know. Just let me know if that happens again. Okay. Let's see. Wait a minute. Okay. Still there. Hmm. Okay. Can we still see them?
Nope.
You cannot see them. Okay. Huh. All right. I'm going to, this time I'm going to try something a little different. All right. Now they're visible?
Mhm.
Okay. Okay. So what we do, we divide each of our compartments xi into n+1 subcompartments. So for each xi, there's n+1 xi k's. So and we start the k's at 0 and we go up to n, so there's n+1 of them. And this will create n+1 ODE systems. So we start with a system of n equations, and we end up with n+1 systems of n equations. All right, it's all right. So I'll describe what this the general format of all this, and then I'll dive into an example. Okay, the first of these systems is this one. I like to call it the source system, and as I described before, these right here are the inputs, and they're being multiplied by a heaviside function, and this just acts as an on-off switch, and this is just turned off until t reaches a t naught plus h, and t naught is a time of our choosing. Oftentimes we choose 0, but sometimes we like to choose a later time. And what this does is this just delays the inputs just for this source system, and then puts it and then just allows different systems to have these inputs while this source system is denied them. Hopefully it'll make sense a little later when I show some example in the graphs. And the reason I like to call this the source system is the initial conditions for this system are the same initial conditions as the original system of ODEs. So for all the before we break everything down into compartments, we have a set of non-zero initial conditions, and those are the initial conditions we use for this. Now the remaining systems are defined as follows, and here the for the xi-k's and where k's not 0, the inputs are being multiplied by the heaviside function, except this time we have a t naught plus h minus t. The orders. So here this is switched on at first and then off after t gets bigger than this. So basically, this source system is giving a little bit of an initial pulse to this system right here. Or actually, I should say these systems. And and the other big difference between these two is these have non-zero initial.
Did the internet go off?
I think maybe so. Let's see if Seth joins back again. Hi, Caitlin.
Okay. There you are.
Did I disappear?
Yeah, I think maybe your internet cut out.
Oh, it's not great. All right. Well, I'll break my slides again. We'll just keep going. Okay. All right. Is this the last slide that you saw?
Yes, I think it was. Yes.
Okay. Okay. So, all right. Okay. So, before I broke the systems into pieces, we had this as an Fij, where this would be the intercompartmental flow rate from compartment J to compartment I. But now we have the subscripts Fik, Jk. Well, what that means is the flow from compartment I to compartment J of material that originated from compartment K, or I like to call it the K source flow from I to J, excuse me, from J to I, and this is how it's defined. Okay, so now we redefine our storage matrix in a I want to say a similar manner to what we did before in that example with the with just the linear algebra, but except we didn't do linear algebra here. What we did is we just kind of went around that, and now we're just filling in each entry with these elements. What we do is once we get let's see, once we solve the system and we get, let's see, is the compartment, the compartment I, subcompartment J, and we integrate that for let's just call it all time, and then and let's see, we divide that by the integral from time zero from let's say t0 to t0 plus h, and plus any source input plus any initial flow from I to j, and then take the limit as h goes to 0. And let's see. Now this, of course, we're doing this on a computer, so we'll take we'll take a small value of h instead of infinity here. We'll take t0 plus m up here. I think this is kind of a substitution, if you will. All right. So with that being said, this whole system right here, pretty messy. I think it's easier to understand with an example. All right. So we have, what we're going to do is a simple ecological toy model example, system of three equations, and we'll call our state variables P for phytoplankton, Z for zooplankton, F for fish. And we'll say our only environmental input is something that comes from the environment, and it's a positive growth rate for the phytoplankton, and all the G's and the subscripts, that's all grazing rates based on what can eat what. We're just assuming zooplankton can eat phytoplankton, and fish can either eat zooplankton or phytoplankton if they wish. And all the D's here, these are all linear death rates for each species. So we'll just keep that nice and simple. The whole model's the model is linear, straightforward and pretty straightforward. Let's see. So and I'll mention just to start. P is x1, Z is x2, and F is x3. Okay, starting to break this down with our technique. Let's see. We'll have our source system right here, and okay, and let's see. Since we have a system of 3 equations, we are going to break it down into n is 3, so we're going to break it down into 4 systems. So our x1 0 is p0, or x2 0 is z0, and so forth. And our only input into phytoplankton is mu, so the mu gets multiplied by our Heaviside function. Our input into zooplankton is the G, GPZ, the grazing rate of, let's see, of zooplankton feeding on phytoplankton. And of course, the rest are outputs. So in blue, this part is being multiplied by the Heaviside function, and there's 2 inputs into fish, so that part gets multiplied by the Heaviside function. Okay, so this is being sent to a specific destination into subcompartment 1. Just from the phytoplankton equation in subcompartment 0. That's being sent here. The Kronecker delta here, that one, those are just kind of bookkeeping devices, just to make sure that we just keep track of where of where things are sent. So basically, like I said, these have the same initial conditions as these, and these have initial conditions of 0, but they do have a pulse of biomass that they got, that's being transferred over from the source system. And then from here, we solve this system separately just to see what happens when this stuff gets transferred over from the source system. So here, this is how we would this is where we get the biomass we would need to calculate that's like the zooplankton storage that's sourced from phytoplankton, and the fish and the storage in fish that's sourced from phytoplankton. And it'd be a similar, it'd be this same type of story from zooplankton. This in blue here, this is being sent to the subcompartment 2 down here, hence the Kronecker delta 2,2. And this is how we would get this is what, once we solve this system with 0 initial conditions, but with some input that's transferred over from the source system. This is how we would compute the fish storage that originated from zooplankton, and the zooplankton storage that would originate from zooplankton, and so forth. And let's see. Of course, I also have the just as visual aids. I have the No, I've been notation spelled out for the P1 is x11, the Z1 is x21, and so forth. And likewise in the last equation, these initial inputs into fish, that's being sent to the third equation, and then of course this, and then this would be this is the only mass that the biomass that we would have, such that this equation is solved. All right, once that's all been done, what we do is we solve this system. Now we can compute each element of our storage matrix, every row, every column. So just as an example, we wanted to compute the storage from zooplankton to phytoplankton, from the formula I showed you before. It would be, the integral on top would be x12. The integral on the bottom would be f2010. And if you wanted to look back through the equations in the previous slide, you could, but I did that for you. X12 is P2, and hold on, I have this, okay. And F2010, the Ask AI Assistant, there it is, okay. The F2010 happens to be the grazing rate of zooplankton on phytoplankton times P0 T. Okay. Every time I go full screen, I seem to, my slides seem to get lost. So, so every time, I'm sorry, when I move to the bottom of my screen, the Ask AI Assistant keeps popping up and gets in the way. So that's why I'm pausing. Sorry about that. Okay. So just intuitively, this is storage from zooplankton to phytoplankton. So what, as in biomass that moves from the zooplankton compartment to the phytoplankton compartment. So just let me just ask the question: do if mass is moving from the zooplankton compartment to the phytoplankton compartment, that would imply that phytoplankton are eating zooplankton, which should we expect in row 1, column 2 of the storage matrix to be? What would y'all think? Anyone have a guess?
I simply don't want to give a bad guess.
You don't want to give a bad guess? Okay. Let me ask you this: do phytoplankton do phytoplankton eat zooplankton, or do prey eat predator?
I think I would need some more hints, but go ahead. Sorry.
Okay, prey don't eat predator, so you wouldn't expect biomass to transfer from predator to prey. You expect it to go the other way around, right? So you wouldn't. So I would expect in the storage matrix, row 1, column 2 to be 0, and turns out row 1, column 2, that's what we get. Given the following parameter values, if we solve that, if we break down that ODE system and solve each of these systems and each of those subsystems and compute the storage values, this is the storage matrix that we get. And I should have mentioned this before. Take this system and take each of the equations of the subsystems, add them all up together. You should get the original system. Otherwise, if you don't start coding yet. So anyway, so this would so this tells you, let's see, So that storage matrix would tell you, let's see, hold on. The source flow, oh, come on. Okay, row. Okay, this would be storage. Okay, yeah. This would be long-term storage in zooplankton that originated from phytoplankton because it's S12. Okay, move along. This is what the let's see. This is what the time series of the time series solution of those four subsystems would look like. So here with the heavy side function that would cause a dip in the source system, but they would call it. But then we have initial pulses in the other four. So this is what we would use to compute the storage in, let's say, like the zooplankton storage that could come from the source in phytoplankton, or say the storage in fish that's sourced from zooplankton, and so forth. And if you add these four together, you're going to get a steady state, basically straight lines. Okay. Okay. Before we go on to the nonlinear system, any questions so far? Okay. I'll move on to the nonlinear system. All right. So, anyway, with the nonlinear equations, we approach this in a similar manner. There's just one problem we do have to get around, and it's kind of it's just something you have to watch out for. Thing is, here with one kind of nonlinearity is a product, which wasn't something we had to worry about in the linear system. All we had to do was just for each state variable, once we're in a subcompartment, just change the number to change just go with, I'm sorry, just use the subcompartment number, the same one for each state variable. But it's not so easy with the nonlinear system. So there's something you have to watch out for. When you have a product, let's see, you have, for instance, PZ, each compartment is the sum of all of its parts. So you multiply the two, with the distributive property, you get a big mess. It's not immediately obvious which goes in which compartments goes in which subsystem. So you just have to it all boils down to just remembering just how you're defining the case source flow from compartment J to compartment I. So let's see. So for instance, the portion of Z that's sourced from PZ and F, it happens to be just the ratios of Z1 over Z, Z2 over Z, and Z3 over Z is what it turns out to be. And the reason why that works is, let's say for the P source flow from Z to F, boils down to this definition that we had earlier. Okay, let me see if I get this right. Let's see. The Fij part, that's the flow rate. That's the grazing rate times the product, and then the K subcompartment, that's this part, and then and then just the XJ compartment. That's this part. And then what we have, that now you see, just we have two z's that cancel, and we just end up with GZF times Z1F. So all you really have to do is just the first factor is just going to be just going to stick with the subscript of the subcompartment that you're in, and the second factor is just going to be the sum of all of its subcompartments. And let's see, for the Z source flow from Z to F, it's just going to be GZF times Z2F, and similar with the fish source flow from Z to F, just from a cancellation, GZF times Z3F. So basically, to put it simply, once we start with this system and we start breaking it down into subsystems or subcompartments, if you will, just take every time we have a product, if we're in a subcompartment, for first term, just use the subscript for the subcompartment that you're in, and the second factor, it's the whole state variable of the original one. Okay. Other than that, it's really the same concept, and really we're really doing the same thing in linear models. It's just in linear models you just don't have to think about it. So here our environmental input function is, I mean, it's time dependent, but still that still doesn't change the fact that we just multiply that by our Heaviside function, and with the other parts of the model, just the inputs, any input into that compartment, any initial input into that compartment gets multiplied by the Heaviside department, so they can be transferred from the source system to the other three systems. And in same way we did with the linear system, anything that's sourced from the initial input in the phytoplankton into phytoplankton gets sent to subsystem 1. Anything that's the initial input into zooplankton gets sent to subsystem 2, and anything that's any initial input into zooplankton gets sent to subsystem 3. And then what we end up with for the following parameter values, these oh, wait a minute. These are also the parameter values for Kazantzis and Ma. This was the paper I told you about at the beginning of the talk with the no, what was it? It was the I'm sorry, I'm blanking here. It's the agent-based model. Okay, it was the agent-based model. This is the same parameters they use. Okay, and these anyway. This is the storage matrix that we end up getting, and here is the here's the time series of all the state variables in each of the subsystems. Of course, here we're not going to get a steady state because it's a nonlinear model with sinusoidal forcing. But okay, this may be a little small on your screen because last time I gave this talk, I was doing it in person. It was on a big screen, so I apologize if this is a bit small. But this, what you're looking at here, is each component of the storage matrix as a function of T naught. And now, notice it's not a function of t. So what I mean by that is, remember this is this, okay, like for instance, I said we can choose any initial starting point t we want. So oftentimes we pick 0, but we can choose other times if we like t20, like 25, let's say days or 50 days or any time we want. And the reason why we want the flexibility is for models like say like a nonlinear model with oscillatory solution. So if we pick time 0, then the long-term storage in entry 1, it's going to look like it could be about a 5. But if we choose time initial time to be 25, it's going to be lower. I think in our linear models, these are all straight lines. But anyway, it was this result that matched Kazantzyan Ma's agent-based model result, and this is all just simply with ODEs. And so that we are very pleased with. And let's see. Okay, so it's 4:50 already. Okay, so just to wrap up, so now we can with what we can do is with any system of ODEs, linear, nonlinear, autonomous, non-autonomous, whatever, we can track the storage in any compartment from any origin and beginning from any interval of time. So and we like that flexibility, and this says it's endless applications in ecology. We can answer all kinds of questions with this, like say how like from an initial pollution source, how this it's a pollutant feeds through filter through an ecosystem. How much time? Where is that pollutant going to end up? Which compartment is it going to end up in long term, or something like that? I'm going off script here. So in the future, perhaps we could apply this technique to things like through flow analysis or cycling index, or test our technique with case studies that involve data. And with that, here are some references, and I would like to open the floor to questions, and I thank you for your time.
Awesome. Thank you very much, Seth. That was a really interesting talk. It's really cool to see that you could match those results too, I think is pretty neat. So let's all thank our speaker. I'll click the clapping emoji here. There we go. So yeah, with that, I guess, yeah, if anybody has any questions, please feel free.
Yeah, I have a quick question, Seth. Thank you for the very wonderful talk. So, yeah, so would this work? Have you have like any like preprints that maybe one could read about to kind of get familiar with this kind of method?
Let's see. We're writing up our results right now. We do have some preliminary results that predate our non-linear results, but it's quite informal, and I don't think my collaborator. I'd have to ask my collaborator if you want to share it now. But we are in the process of starting a manuscript right now.
But you did mention a paper earlier that you guys kind of used to kind of model, like kind of look at your simulation to compare with. Did you mention a paper?
I see. Okay, right here. Kazansi and Ma, this was the why do I keep forgetting the darn I probably haven't done much work in it, but it's the this is one with the agent-based model. And also, as far as some of the let's see, at least that paper, let's see, what they do is it starts with that paper starts with this explanation, and gives you that, and they say, okay, what do we do with a nonlinear case? Let's do an agent-based model, and then they eventually get here, and then so if you're interested in reading about that, Kazansi and Ma would be a good that'd be a good paper to read. This is from 2012 ecological modeling.
Oh, thank you. Thank you.
Any other questions? I maybe had just a quick one, Seth. Do you think that this could apply to carbon capture methods? I know that there are people that are looking at either through chemical reactions or other means to store carbon in the ocean. Do you know of any like possible application that might not be necessarily ecological, but
I see the potential there.
okay.
This is more about the method than it is about an actual model. So yeah, I definitely see someone attempting that. Matter of fact, I mean, I don't know. Someone might even try to attempt to do this with PDEs or something. We'll see.
Okay, interesting. Cool. Okay, yeah, it's always fun to see how math can be applied all over the place. Yeah. Okay, any other questions for Seth? Okay, well then let's thank Seth again, and I'm sure if you come up with any questions afterward, you could send him an email. So thank you, Seth, and I think next week we do not have a talk, but we should be picking up again after that. So thanks, everyone.
Okay, great. Thanks. Thank you, everyone.
Thanks, Seth.
All right, you're welcome.